Hi, I'm Zhongle Tian, and this video will be the presentation about the details of experiment T3, which is thermal equation of state and critical point for Physics Laboratory Year 2 Semester 2. And I will continue introduce about the objectives and procedure for this experiment. The objectives of this experiment aim to demonstrate the principle of gas cooling by expansion and also the throttling process, finally the Joule-Thomson principle. The operator needles in this experiment included Joule-Thomson apparatus, temperature probes, digital meter, carbon dioxide and nitrogen gas supply. First of all, digital meter had been switched on at least 30 minutes before any measurement. The temperature probes T1 and T2 were connected to digital meter correctly and LED indicators were turned on. Carbon dioxide gas will be indicated first. All the pressure valves which were gas cylinder valve, reducing valve, and operating valve were checked to be in tightly closed conditions. Then we will check the actual direction to turn on and off this knob. The rubber tube was connected tightly from the carbon dioxide steel cylinder to Joule-Thomson apparatus to prevent the gas from leaking. Next, we will adjust the pressure by reducing valve to pressure of 0.7 bar first and record the change of temperature by pressing delta T buttons on the digital meter after 1 minute. After that, the pressure was reduced by 1 bar and step 5 was repeated until 0 bar of pressure is get. All the valves was closed and replaced the rubber tube of carbon dioxide steel cylinder to nitrogen steel cylinder. The rubber tube was again connected tightly to Joule-Thomson apparatus. Last but not least, repeat the steps used for the measurement of carbon dioxide, but replace the maximum values of pressure from 0.7 bar to 0.8 bar for the nitrogen gas.
I'm Fatin Roberta Davia Binti Salihuddin. Thank you for my groupmate. So right now I will explain for you about data analysis for this experiment. From this data analysis, we uploaded graph of temperature difference versus pressure. Also, we obtained value of Joule-Thomson coefficient of carbon dioxide and nitrogen gas. And the last one, we will compare the value of coefficient between experimental and theoretical. So before we uploaded our graph for carbon dioxide gas data, from the data that we are recorded in the table, the value of pressure, we are total it with the atmospheric pressure, and then we can see that we use a different value of pressure from the highest to the lowest, and also we can see the difference of temperature is decreased along the value of pressure. Then I use the least square method to determine the best way fitting a chart of a data point for our data. So from nitrogen gas data, I also imply the same way, which is the value of pressure is the total value of experimental pressure value and atmospheric pressure value. We can see that the value of pressure we use is different from the highest to the lowest, and the value of difference temperature is decreased along the value of pressure. So like you can see the graph of the difference temperature versus pressure that we uploaded. The top straight line graph is a for carbon dioxide gas and the bottom straight line graph is a for nitrogen graph. So from this graph we can obtain the value of gradient, and that means we also can determine the value of Joule-Thomson coefficient for the both of graph. From the equation given, we can know this experiment is constant for enthalpy process. So the value of coefficient Joule-Thomson coefficient can define by the equation. So for the value of Joule-Thomson coefficient for carbon dioxide, we determine as a 4.0 exponent -6, while the value of Joule-Thomson coefficient for nitrogen gas we can determine as a 3.2468 exponent -6. So next, I need to substitute the constant given into the equation 6 to make sure that I get the value of theoretical value for Joule-Thomson coefficient for carbon dioxide and nitrogen gas in the room temperature, and then I compare it with the experimental value for our data. So the percentage difference for Joule-Thomson coefficient of carbon dioxide, we can get 48.8%, and for percentage difference of nitrogen gas, we can get 13.9%.
From the data, we can see the pressure affecting the changes of temperature. From the graph of temperature difference against pressure, we can see that the gradient of the carbon dioxide is 4.006 exponent -6, while the intersection of y-axis C is equal to -5.2959 exponent -1. And for the nitrogen, it's different, which is the gradient is lower, 3.2380 exponent -6 Kelvin per Pascal, while the intersection of y-axis C is equal to -5.8581 exponent -1 Kelvin. Now, by comparing the theoretical data from the formula of van der Waals and Joule-Thomson, we combine them to make a calculation. We find some differences between theoretical value and the data we get. To know that the gradient of the graph is the Joule-Thomson coefficient that we can compare with our data to the theoretical value. So the theoretical value say that the Joule-Thomson coefficient C for carbon dioxide is 7.8169 exponent -6 Kelvin per Pascal, which for our data it's quite bit much further from the theoretical value, which is 4.006 exponent -6 Kelvin per Pascal. So if we try to make the comparison, we get the error of 48.8%. Now we're gonna look at Joule-Thomson coefficient for the nitrogen, which is for theoretical 3.7744 exponent -6 Kelvin per Pascal, which is in our data we got 3.2380 exponent -6 Kelvin per Pascal, which is very good because when we do calculation we get the percentage of error of 13.9%. For precaution, make sure that there is no parallax error, so your eyes need to be perpendicular to the reading scale so you can read it properly, so to avoid parallax error. Second one, the connection of gas might be not good, might have a leaking gas there, so make sure that you connect the gas connection firmly. Until there's no hush or any sound leak of the gas. And the last one is make sure that you make the changes of the pressure fast and shortest so you get the reliable result.
In conclusion, Joule-Thomson coefficient for carbon dioxide CO2 will be 4.006 times 10 to the power of negative 5 Kelvin over Pascal, and for nitrogen gas N2, it will be 3.238 times 10 to the power of negative 5 Kelvin over Pascal. Throttling process and Joule-Thomson principle have been demonstrated in our experiment as the temperature of gas being cooled in condition of no heat transfer when expansion occurs. Furthermore, positive value of Joule-Thomson coefficient indicate the cooling of gas when the gases are forced to pass through the throttling point. That's all from our presentation. Thank you.